divination that you did about it.
Yes, some divination about mathematics and chaos theory. But anyway, hello all to the people in the future who are going to possibly watch this, or possibly no one. Who cares? This is part 3 of our Emergent Hangout hangs following the Coursera course. Obviously, if you're tuning in, that should be pretty obvious. And today we're going to be talking about chaos theory. So, Cliff, you want to maybe start off on a topic, or do you want me to throw out something?
So yeah, okay. So basically, just give a very short introduction. What they covered in today was a follow-up, of course, of material that they've been doing before, and essentially introduced what the concept of chaos was formally. And they talked about the concept of an attractor, and they gave a couple of very simple demonstrations of both concepts.
Cool.
Now, could you define an attractor for the audience?
Well, basically, what an attractor is, essentially, it is a set of points. They usually talk about it in phase space, but it doesn't matter. But essentially, it's a set of points in some kind of coordinate system through which any initial points will try to evolve towards. That's why they're called an attractor. Because whatever the initial conditions is, they will essentially be attracted towards a certain point or set of points in a coordinate system. So you see a pattern emerge as trajectories move towards those points.
Yes, and so the other interesting thing about attractors is that they're what's known as compact. So where they occupy a finite space, but they are constantly moving inside of this space. So where, and that's why it's called attractors, because there may be multiple attraction points, and the attractors actually can be of different dimensions. So there can be single-dimensional attractors, which are kind of the most trivial case, as well as two-dimensional attractors, which I haven't really seen many, but most attractors I've seen are usually occupy some sort of three-dimensional phase space, and there's a lot of them. So the classic strange attractor is obviously the Lorentz attractor, which was interestingly enough based off of a very simple model of convection currents. And so if the three dimensions of the phase space are the rotation, so if it's going counterclockwise or clockwise, and so the further out in one direction that you go, the speed will be faster. So if you go out to the left, it'll go really fast to the left, and if you go to the right, it'll go really fast to the right. But if you approach the origin, it'll slow down and then stop and then reverse as you cross it. And then the other two dimensions of the phase space are the inversion of the heat, so where you can actually invert the heat so that it goes to the top rather than the bottom, as well as what was the third dimension? I had it in my head, but I completely forgot it.
It's the gradient of the heat from left to right.
Right. Yes, exactly. Yeah. And so those three simple variables create what's known as the Lorentz attractor, or actually what's colloquially known as the Lorentz butterfly. And maybe someone wants to screen share an example, or who knows? All right. So one of the defining characteristics of chaos theory is actually nonlinearity. So an example of linearity would be like turning up the volume on someone's microphone, where you bump it up a percentage, and the percentage of the sound, or the volume of the sound, increases linearly with the increase of the knob. While something that would be nonlinear would be well, gosh, plenty of things. An avalanche is a perfect example of a nonlinear system. Maybe anybody else have some good examples of nonlinear systems?
We're all familiar with nonlinear systems, right? Like tax is a nonlinear system, like interest is a nonlinear system.
Exactly, right? Yeah.
But the interesting thing, right, so this has been around for quite some time, just like in general math, going back to Poincare, but it came about an application-wise from Lorentz, of course, was the name, who was studying weather systems. And like many things, was discovered completely by accident. So here's a guy doing weather modeling, So he runs a simulation. Then he goes out. He has his numbers written down for his simulation. He puts the numbers back in again to run the simulation again, like that you would for a number of things. Of course, just checking, and his results comes up completely different. And what he found was that really, really tiny changes in his starting points produce completely divergent behavior. And he was measuring to 1 part in 1,000 and couldn't get convergence. Now, many people have like sort of weird ideas about what scientists do and what they don't do. Measurements greater than 1 part in 1,000 are relatively rare because you have to consider variances in absolutely everything. And so what he was finding is like systematically it's very difficult to measure beyond that. So the problem then becomes, well, how could you know anything, right? Like if the system is so chaotic, using the colloquial version of the word, that you can't measure enough precision to eventually ever duplicate an experiment, because every time you run it, you get different results. Well, then how do you analyze it in a scientific way? And that's where chaos theory comes from. Like it's a way to look at patterns that don't simply repeat, but you can still get information out of them.
Well, isn't like the thing, if you analyze something that's chaotic and you see something that doesn't appear to be chaotic, doesn't that tell you something new about it?
Well, it can be a chaotic system, but where so most chaotic systems when they are in what's known behind the chaos point, or I don't know if that's the proper term, but you can have chaotic systems that can be highly regular, but they become chaotic when you adjust the variables, such as with the weather system, increasing the heat to the point that it becomes chaotic. So you can actually have multiple modes to a system where one is completely stable, one's may not be even either stable or periodic, and then as you adjust the variables, it then eventually becomes chaotic. It leaves either the periodicity or the stability and goes into unpredictability.
Yeah, so the thing that's really critical, like the main thing to understand, is that the unpredictability means you can't exactly replicate the same results. You can never ever get the same results out of an experiment again. And it's never possible to constrain the information that you're putting in to get like exact information coming out. And because systems can be so nonlinear, you could have, for example, that you put you have like you measure to 1 part in a million, which is absolutely fantastic, but 1 part in a million produces divergence. It produces differences on the scale of 1,000,000%, which is crazy. You wouldn't expect that, right? So when you have systems like that, you can't get exact results. So what you end up looking for is patterns. So you get something that's cyclic. How do you get information out of it? And that's what people started to look at. Like, what are the patterns that are formed in these things? How do we figure out what's going to cause these patterns, and how do we analyze them? Because you can't analyze it like by the trivial method of let's just generate the same things because we know what's going to happen at point T. You can't. You can sort of figure out a pattern that's going to happen. That's what you end up having to look for. And the other really interesting thing is that these very complex behaviors, which can be like really complex to look at, can come from like the simplest rules that you would imagine, and you can get these really complex structural patterns coming out of equations that you can write down like simply like in 1 or 2 steps.
Right, and a really good example of that was the Boids that we talked about in our first hangout, where you have 3 very simple rules. I'll just go over it again really quickly, where for each agent in the simulation, it follows these 3 rules at every iteration step, where it goes the same direction that everybody else is going, or tries to change its direction so that it's more in line with the average of everybody around it, to go at the same speed that everybody's going, and to also maintain a little bit of distance from everybody around itself. And those 3 simple rules create a very complex emergent chaos, not specifically chaotic. Well, it is chaotic in the sense that it's very sensitive to its initial conditions, but it's also very ordered in the sense that you get a simulation that is very similar to birds flocking from just 3 simple rules.
Right, and I think that's the problem, or that's essentially the point that I would like to see come across a bit more, because oftentimes in a lot of these discussions when people are talking about mind or evolution or some such thing, they'll look at it and they'll think, like, this is a very complex thing. There's lots of structure here, so it must require something very complex behind it. Like, however we understand this is going to be if you write it all out, this big book filled with this big bunch of rules. And what people are finding is that often it can be the case that you can write down the rules behind this that are really, really simple. And from like rules that you can write down literally 1 or 2 sentences, you can get very complex patterns that come out of it. And if these complex patterns are in living things, then they can produce what appear to be functional or design behavior.
If I could just add, I took a course called ethnomathematics, and it seems like the same idea was applied to, I guess, fractal patterns in different cultures, art, and like ceremonial paraphernalia. Like you could just start from like 3 rules that you draw a line from the middle, and once you reach a certain square and like a certain tile, say you're drawing this on tiles, once you reach a tile, you curve up, and then since you're curving up, you draw a line again, and then if you're heading up, you invert the curve. Just little simple rules end up making these very intricate, like interesting looking patterns and works of art that are seen cross culturally. It's kind of interesting.
Oh, exactly. Actually, and this leads right into one of the examples in the talk, which is where you create 3 points, and then you randomly roll dice, and that dice will tell you to approach. You go halfway to the labeled dice or the labeled point that's associated with the dice, and you do this random iterative process, and you would think that you would just see a mess of points, but what actually occurs is that you have a Sierpinski's triangle that comes out of the this random process.
You know, I put an image of it just in the side there, so I generated that. It's like 30 seconds of Excel code. And there's 3 triangles that will come up in the image. The first one, I think, is 100 points. The second one is 500 points. And the second one is 20,000 points, I believe.
You should screen share it.
Yeah, here you go. I am. Do you see that? Yes? No? I think it's probably still loading.
I don't see anything.
Just black.
Still your regular thing.
All right, let me try that again. Yeah, it's just my regular thing for some reason. It seems like screen sharing doesn't want to work today. Okay, maybe someone else screen share that if you could. I'll present you.
Hey, Cliff, what does scale have to do with anything? Like, what do those points just represent, actually? Like, how can...
Well, that's like essentially one of the defining features of fractals, right? So if you look at that triangle, it doesn't matter what scale it is that you look at. You could keep blowing that triangle up, and the pattern keeps repeating over and over again. So it essentially goes down to the fine structure of whatever it is that you're using. Now, in biological systems, all fractal patterns will break down at essentially the units of whatever it's made out of, like cellular structure or whatever. But that's one of the defining characteristics of a fractal, and it has to do, like, that's the reason why fractals have strange properties. Like, they have non-integer dimensions, which is very weird to think about. Like, you can think about a one-dimensional object, you can think about a two-dimensional object, you can think about a three-dimensional object. What does an object look like if it has 2.7 dimensions?
Oh,
That's kind of weird, right?
You know, and there's also an excellent Wikipedia page. I'll grab it where it actually is a list of interdimensional objects, if you want to call that. I forget what the technical term is. but I also posted an animation of the fractal dimension. That's what it's called. But here we go. Yeah, list of fractals by the Hausdorff dimension. So this goes into the different dimensions that some of these systems have. Let me see. So the Sierpinski triangle has a dimensionality of 1.5849. So it's also the triangle of Pascal modulo 2. So it's kind of interesting.
Hey, I'm sharing the screen.
Oh yes, thank you. Okay, so
Sorry.
yeah, there. I'll present you in just a sec. So yeah, there you go. So that's exactly what we were talking about. So where you have these random points that you have a very simple rule set. So you have the top point, the left and right points on the bottom, and so what you do is you pick a random point somewhere on that graph, and then you roll a dice. If it's 1 or 2, you go halfway to the top point. If it's 3 or 4, you go halfway to the left point. And if it's 5 or 6, you go halfway to the right point. And so you just keep repeating the algorithm. You roll the dice, you measure halfway between the current point and the point that you're going to, and then you mark a dot halfway there. And then you just roll dice again and repeat that algorithm again and again and again and again, millions of times, and you get the Sierpinski triangle, as shown here. Could you screen share that Zoom, that Wikipedia GIF that I posted to you?
So the interesting
Excellent.
thing about this is, right, like you see these, that comes up in biological systems all the time. In fact, one of the guys for the project this week actually took something that he grew in his garden or whatever, and it had a fractal pattern to it. So it comes up in nature. And like when you look at that, if you didn't know anything about chaos or fractals, you think something really complex must be going on behind the scenes to produce that. But now you understand all that requires is something which is slightly random, and then something else which would cause sort of a counterbalancing. So you have a point or something. There's a random effect which makes that point want to move towards one of 3 locations. And there's some counterbalancing, so it only moves halfway between that and the other location. And it's kind of interesting to see, like you could easily think on that as being some kind of feedback system that would evolve in some kind of living organism. Like inside a cell and outside a cell, there's pressure based on the osmotic gradients. And you can see these kinds, now you can make an argument for how physical laws would produce these behaviors with just a couple of very simple physical laws and feedback loops.
Exactly. Okay, so after they talked about Sierpinski, this is actually going off the course now. There was the coupled pendulum that they talked about, which is a you might have seen this toy where it's a pendulum that is actually a circle, and then inside of it there's another pendulum, and so these two pendulums are coupled to each other, and the outer pendulum is completely periodic. It actually isn't affected by the inner pendulum, but the inner pendulum is affected by the outer pendulum, and it's even though the outer pendulum is completely periodic, the movement of the inner pendulum is chaotic. Let me see if I can get a GIF so that you can.
And this would relate to a question that I think Spoken was bringing up the other day about why are we symmetrical?
Oh, okay. Yeah, go right into that.
Right. I can't speak any further into it. This would explain some of that with just very few natural things.
So you mean like our bilateral symmetry that we have?
Right.
Interesting. Well, maybe just really quickly, just what did he say? That would be interesting to go into.
No, it was just that. It was he when he goes out and looks into the world and sees things like that, like that we're symmetrical and things, he's just in awe that doesn't think these things could arise naturally.
Right, that has to be designed.
Right.
Oh, we were actually just talking about this before we got into it, and So yeah, where it seems that flocking of birds has a form of irreducible complexity, or basically any physical system. But it seems that the longer we look into, or the longer we think about it, the deeper we look into it, it seems that the complexity isn't as irreducible as we thought it was. And I'm not able to find a really good example of a coupled pendulum.
Here we go. We got this triangle thing working.
Isn't there there's one on the chaos theory wiki.
Oh, there is.
See, Joe, mine's better.
Is it? I'm
Yeah,
not looking
yours
at
is
the
much
screen.
smoother.
It might be my inner buds.
Your
So stop
mom's is
presenting
much
me.
smoother.
I did. I
Is that-
switched over.
Okay.
Here we go. They're not. Technically, it's a coupled pendulum, but apparently they're called kinetic perpetual toys. So here we go. Here's
Right.
a good example. Let me see.
Yeah, whenever you brought that up, that's what I was thinking of. If you've ever watched those videos on perpetual energy machines that people will build little models out of wood and thing, the pendulum
Yeah.
that you're talking about shows up in a lot of them.
Yeah, here you go. If you want to,
This thing is
Put
really
that-
easy to stare at indefinitely.
right? Yeah, they're
It pisses
great.
me off.
Yeah. Here, Ocean, do you wanna broadcast the link I just posted?
Let's see.
So this is the coupled pendulum I was talking about.
Let me define areas.
Yeah, there you go. Excellent. So the outer ring is is going to always be periodic. What happens is that at the bottom you can see there's a magnet, and there's a magnet in the base, and that magnet gives the system a little kick every single time the magnet passes over it. And so the outer ring is going to be always periodic. But the fascinating thing is that these inner rings, which is just a single object, as you can see, there's a 45-degree angle that couples it to the outer ring. But the inner ring is going to be completely chaotic. It's very highly sensitive to its initial inputs, and there's essentially no way to predict the movement unless you have a completely perfect description of the system, which obviously nobody does.
Well, that comes up with a point that Helena was talking about last week, and she brought it up essentially the week before, because she was wondering when are they going to start talking about when views from reductionism will fail. And a reductionist approach is very difficult to take to analyze the motion of even very simple systems, like a two-body connected pendulum. The simplest one is you just take one pendulum, you just attach another one to it, so you have two simple masses. And from a reductionist approach, that's extremely difficult to do anything with. Even someone who's relatively skilled in calculus and physics looks at that and goes absolutely nowhere with it. So in order to analyze systems like that, you need a completely different way of looking at it. And you need to look at so again, you're not trying to find out like where it's going to be like at time t equals some set 710 seconds. What you're looking at is what kind of pattern will be produced in that. What's the order of repetition of the pattern? What's the period? What does the pattern look like? And then you look at, okay, what is it about the system which produces these patterns? And we're gradually now starting to learn to recognize from a pattern that we see, what are the underlying characteristics of the system? Like, what would the rules be in order to produce these patterns? And that's sort of what the math is sort of looking at now.
Interesting. So I was just looking up pictures for the next topic that we're going to have. So the other thing that they mentioned was the three-body problem. So Ocean, if you could...
Yep, working on it.
All right, thanks.
What about
Excellent.
this guy?
Yeah, exactly. So this is the three-body problem. So classically expressed, the three-body problem is the question of, is it possible in a Newtonian gravitational situation, such as the one that we're viewing here, that we can have a stable orbit of three bodies? And it still seems to be an open question where it's not quite known whether or not there is a solution to, or that the solution being a stable orbit of three bodies. Now the interesting thing is that intuitively we should be able to find a solution, because obviously there's the many body solution of like our solar system. Our solar system is a massively complex system of interacting bodies, but yet it is actually surprisingly stable, highly stable. I mean, it's been stable for millions of years. But yet mathematicians themselves have essentially not been able to find a stable orbit of three bodies because of the high amount of dependence. But interestingly enough, it does seem there are some solutions. I'm now looking at some pictures. There does actually seem to be some solutions to the three-body problem. Interesting.
Are you talking about three bodies of equal mass, kind of
Yes.
having a cohabitating orbit with all of one another? Because you have like binary stars, and
Yes.
then when you have orbits of planets around said stars, it's usually kind of operates as a two-body structure anyway. And
Yes.
the solar system is a many-body interaction, but it's still each body is interacting mainly with the second body or with the primary body rather than with each other. Is that what you're saying?
Right. So
There's a
the
problem
critical
when you
thing,
get
yeah,
three.
the critical thing to realize is that what they're talking about is there's no closed form solutions to any of these problems. Like you could
Well, that's
easily
a
write
conjecture. That's
Right.
that hasn't been proven formally,
Right.
but
known to now, right? Just mean we don't have any closed form solutions. Whether or not
Right.
they exist is something else. So
Right.
you can put very simple things together. Like this is just three masses, right, that attract towards gravitation. So you would assume, I mean, gravitational law is like the simplest thing you could think of, right? Like it's just two masses divided by a distance between them. And the
yeah, inverse
force is-
square. Yeah.
Right. It's directly along that line of contact. The problem is that as soon as any one of the bodies moves, it changes essentially the vector field. It changes the way the things would actually move.
Yeah, ocean. Yeah, go to that other one. So this does actually seem to be a proposed solution to the three-body problem. That does seem to be a stable orbit. Now go to the other one too. I posted another seeming solution too. Yeah, there you go. So that also seems to be a solution to. Oh no, yeah. Oh no. Yeah, there you
That
go.
one, the white
No,
one.
yeah, that one.
there
Yeah.
you go.
So that also seems to be a solution to the three-body problem. But that seems like a very unnatural orbit. Obviously, I mean, if we were to see something like that in space, that would break apart very quickly. That it's only a solution because those are the only three bodies interacting.
Yeah. The issue with adding a third body in there is that the push and pull, right?
Exactly.
You're going to throw one off, then you're going to have to counter that somewhere, or it's going to not keep orbiting, or they're going to crash into each other, kind of thing. Two of them would
Right, and
I'm
this
sure
is an
there's probably
even.
it's probably a lot easier to have two or even four, but I see
Right.
an issue with.
Yeah, that's an even more elegant solution actually to the three-body problem.
Mhm.
And the interesting thing is that if any of the parameters were just slightly off, it wouldn't be a solution. I mean, the parameter could be 1/1,000,000% off, and it would not produce these stable orbits. It eventually would go into chaos.
It's just collision.
And that's
You
a
retain order some
fascinating
other
thing.
way.
That's a fascinating thing to think about too. Is that chaotic systems can have. So what this is known as is a fixed point. So this is a fixed point in the phase space, basically. It's that's the solution basically to the three-body problem. But that fixed point is a very kind of perched in the phase space at a very kind of precarious position, because any perturbation to the initial starting positions, it would no longer be considered a fixed point.
Right.
And so kind of to go back to the the coupled pendulum, there's also not only coupling pendulums to each other, but you can also couple pendulums to magnets as well. Let me see if I can grab a. Here we go. Whoa.
But the real question is, how
Yes.
do magnets work?
Yeah.
I had a clown ask me that once.
Yeah.
Yeah. Here you go. Ocean, go ahead and
Oh God,
screen share that if you could.
this is
Now
just.
we know.
Is it supposed to be a wall of gibberish text?
Oh,
Now
I,
we
I
know.
know. I don't know. For some reason, it did that to me too. Okay, let me just find a better picture. Cause yeah, it just was a wall of gibberish for me
Now
too.
we know that magnets work on chaos theory.
No. You can create a
Chaos
chaotic.
magnets, bitch.
You have to
Yeah.
download that image on that IC. You can't. It's not a clickable link like that.
Weird. Okay, let me
I
let me
ain't
see
doing
if I
it.
can.
I am too lazy. This USB port has a big fucking stop sign on it. I don't give a fuck about your stop sign, bitch.
I can't find a better example than that one. That was actually quite a good example of
Let me see what I can do with it.
Yeah, see if you could download it. That shouldn't hurt too much. But so the whole idea is that you have a series of randomly placed magnets on the table, and then you have a hard
Yeah, here you go.
stick pendulum where the pendulum actually isn't on a rope; it's on a stick. Oh, there you go. Yeah,
Oh
thank
shit!
you.
I closed it. Sorry.
That's
Send
Give me
it
a
to me over.
second.
Send it to me over Skype. Xbox.
Yeah,
It's
hang
fine.
on.
Xbox is gonna present in just a second. He's got it up.
His presenting
and-
sucks though. Send it to me over Skype.
Yeah, I'm gonna send it to you on Skype.
Oh, okay.
It'd be easier for him to screen share. I only have one monitor going right now.
Oh, okay.
Yeah,
Sounds good.
I've got two monitors and a screen sharing program.
But yes, so the whole idea is that you have this this pendulum, this stiff pendulum, and that again you have this very highly sensitive system that's highly sensitive to the initial conditions. So where as the magnet as it's beginning to swing, will approach the first magnet. There you go. And so that magnet will be repelled from that magnet that's approaching it. So it's either going to go to the right of the magnet or to the left of the magnet. And that first choice, well, it's not really a choice. It's completely determined. That the way that it goes will be essentially the initial chaotic input that makes it extremely difficult to determine the direction of the magnet. And obviously, having multiple magnets underneath it will cause it to have a more chaotic swing and all these kind of things. But again, another system that is highly sensitive to its inputs. Another example, actually, we can go back to the Lorentz example, is obviously weather. This is a very chaotic system where you can try to create some sort of linear set of equations where you take the let's say we're trying to estimate or guess what the weather is going to be like in Texas tomorrow, right? In Austin, right? So we can try to take an assumption where we take like the wind speed in Oklahoma and we divide it by the dew point of Dallas, and we multiply it by the wind speed in Louisiana or something. Obviously, that model would never work. That's a completely arbitrary set of equations. But the whole idea was that you could model the weather using these very simple equations that had the inputs from these measuring devices across the U.S. But what was found was this whole butterfly effect. This is this very where you could model it for a little bit. You could predict the weather out for a couple of hours, but because the system is so inherently chaotic, the longer you try to predict it, the more your models fail to match reality. And this is probably why weathermen are never going to give us an accurate picture of the weather any more than a week out, if that. Oh, and Xbox actually brought up another excellent example. So, ping pong balls on mouse traps. Um, yeah, what about it, Joe?
It's just like ping pong balls on mouse traps. Haven't we all thought, how does that happen?
Yes, yes. Um, so where and that's actually an interesting because that one actually differs quite from the other systems that we have where there's a high amount of potential energy stored in these mouse traps. Well, where most of the systems that we're talking about actually don't have much potential energy. They're just talking about kind of the sensitivity to initial conditions. Yeah, go ahead and play that video. Oh, wow, look at that.
Well, this is not an organized system.
I'm like seeing the triangle.
Yeah, not only is it not an organized system, how the system reacts is highly, highly sensitive to its initial conditions.
The question that I asked in the on the event page was, if you look at, for example, you ask people to define, like, what's a scientific method or what science is. One of the things they trumpet all the times is, well, if you're going to say something is scientific, you got to be able to repeat it. You got to be able to duplicate. You got to be able to come up with the same type of results. But how many times would you have to repeat that ping pong ball experiment before you would ever get the same results to happen? It doesn't seem like you could ever do that. Doesn't the same would
Exactly.
never ever happen again. So, but the more, when you start thinking about that, but isn't that the way that things actually are? Like, things are not simple harmonic oscillators, right? Actual real systems, real, especially living systems, but even non-living systems, are highly chaotic. So this forced sort of perception that you have to be able to repeat experiments and get the same results seems to be nonsensical. That only holds in very, very constrained artificial systems. So when you
Exactly.
start looking at actual real living systems, I think one of the things that's coming across is we need to change the way we're looking about stuff. And we're not trying to get the same sort of behavior. So we need to throw that out the window completely. So that doesn't mean science is not constrained to being able to repeat something and to get the same behavior as much as it is to look at a pattern and see, can a pattern be actually, can you characterize a system as having a sort of pattern? And that pattern itself will never actually fully repeat like 100% at
Right,
the exact
exactly.
same
The
pattern.
question is, what aspects of a system can you not only qualify but also quantify? So maybe in the ping pong example, we can have a probability that a certain mousetrap is left untouched, or something like that, right? That's something that we could quantify, and obviously the probability would be very low, but it's still something that, given enough experiments, we could definitely give some kind of probability value to. But like you were saying, Cliff, trying to actually describe the system as a whole in a deterministic manner, or to fully quantify it, is essentially impossible.
Right. There
And
might
then
not even, you're right.
we
There
need to
might not
use
even be attractors in that system, right? That system
exactly,
doesn't have attractors in
yeah,
it. But if it had attractors in it, you might be looking at something like, how does the center of mass of that system change over time? So you're no longer looking at individual ping pongs, but balls. But the point is, like, in general, we don't really think about stuff like that. Like, if you look at biology and you're looking at, like, a fish for whatever, or whatever the hell you're looking at, you're generally not looking at like one thing and seeing like where one particular trout is going to be a year from now, right? You're thinking about where a population of fish is going to be, and then more importantly, what the ecosystem is going to be like reacting to a bunch of different pressures put on it. So this is again where I think it's coming back. We're having to look at this from a very different point of view, and it's not coming back from a reductionist perspective. Okay, I will figure out where every trout is, then I'll figure out like how much every trout eats, and I'll figure out how much things eat that trout. You don't look at it like that at all. You look at the dynamics of the system over time. Are there patterns that actually repeat in that? If there are patterns repeat, what does it mean about the underlying physical laws? What kind of nature do they have to have? Where are the attractors in the system? You can see that from the repetition. And what does it mean that it has attractors there? Both in terms of long-term predictions, what can you make out of it, but also what does it imply about the physical nature of the system? It's just a very different way of thinking about problems.
Right, exactly, where the complexity of the system has forced us into creating new tools to quantify and qualify the things that we see. And it's forced us actually into a corner where there are definitely things that we can't say about the system because of our complexity, and it's kind of where, like in chemistry, it's highly deterministic. You have certain inputs and the reaction happens, and then you have outputs. But that's not always the case either. There are actually some highly chaotic chemical reactions as well. Actually, maybe Cliff, maybe some of these chemical reactions off of the top of your head that are chaotic?
So, I mean, essentially, like, you think on that, right? So you take any chemical reaction. It's very easy to calculate the Gibbs free energy and see whether or not the reaction is going to be spontaneous, right?
Mm-hmm.
Okay, so that'll tell you whether or not the reaction will happen at a given temperature. However, it doesn't tell you about the frequency of collisions of a particular molecule. And the frequency of collisions is necessary because you have to have a certain activation energy. Anyway, all that mumbo-jumbo aside, you could look at like two molecules, say. If you had a container that only had two molecules in it, it would be very easy to do a simulation on some kinetics. Just imagine the two molecules bumping around, and you could figure out like how often would they hit each other with the necessary energy so the reaction would happen. That's a very easy thing to do. But now, say if that reaction produced energy, like when you burn something, right, that produces energy. If you light a candle on fire, as the reaction happens, as the candle wax gets consumed with the hydrocarbon, it produces heat. Well, that heat could allow other reactions to happen. So imagine you no longer have a box with two molecules in it. There's a lot more than two in it. So when two starts to react, they can actually make other molecules react around them. And it should be kind of obvious that you wouldn't want to try to calculate what's going on by looking at each individual molecule. Like, you drive yourself mad. There's simply too many variations. It's just way too complex. Even if you only put like 10 molecules in there, just bumping around, you can imagine how complex a system that would be.
Oh, yeah.
But like, real things don't have 10 molecules in them, right? They have millions and billions of things going on into them. So we need a different way of looking at them. And I think that's starting to come out in this course, and they're going to talk about it next week, because they're going to start talking about, okay, so in real systems, how do these things work? What are the physical properties of real systems that produce these patterns, and how do we identify them from the patterns?
Oh, definitely. And the interesting thing is that creating strange attractors and actually empirically measuring certain systems that are chaotic can give us insight into structure. So this kind of segues really nicely into the next topic, which is dripping taps. So where if you have a slow drip, the system is highly periodic. But if you increase the flow rate to the point that it's not full on, where it's not a full stream, but it's kind of gaining speed, and what happens is that the drip becomes chaotic. It becomes unpredictable. And the interesting thing is that empirically these drips have been measured, where they shine a laser through the water dripping down, and what they found is that the distribution of dripping is actually trimodal in the phase space, and you would never, possibly from first principles, be able to explain why it's trimodal, but when it's empirically shown that it does make sense, because there really is three states that a chaotic drip could happen. So the first state is where you have well-segmented drip, so it goes drip, drip. And then there's the second state where you have kind of two drips mushed together, so you have like a dribble, right, where you have kind of two drops, one after another. And then the third state is actually a consequence of the second state, where you have two drips together, but then all of a sudden, because those two drips kind of came together, the the water that pulls away leaves a large gap behind it. So where you get the third state where there's a long gap between the last drop and the next drop because it pulled away a large amount of water, and now the faucet has to catch up with it. And you could never really, from first principles, come to that conclusion. Or I mean, maybe you could if you thought about it for a long time. But it's much easier simply just empirically measuring it, saying, there's a trimodal distribution to the rate of drops, and then induct on that and say that here's the model of how this works. And obviously, you don't even have to induct on it. You can just watch the high-speed camera. But empirically measuring it produces this kind of trimodal strange attractor where there's these three attraction points that are described by the three states that I went over. But that's a rather simple example. And the last example, at least for the examples that I wrote down, is pathological order. So even though it may seem that in a biological system that you want order, that actually can be pathological as well. Where so a really good example of this is Parkinson's disease, where you the shaking that a person has when they have Parkinson's is actually very ordered. There's a certain frequency to it where they're shaking, and this happens because you have the brain in a state of pathological order, where usually the state of the brain is actually quite chaotic, but where there's actually, when someone has Parkinson's, parts of the brain that are usually not synchronized are now synchronized, and there's this involuntary shaking that happens. And that's kind of just the descriptor for such a state is known as pathological order. Another really good example for pathological order is actually when someone has epilepsy, where when you look at an echocardiogram of someone while they're having an epileptic fit, their brain waves are actually extremely ordered. It's a two-phase system where there's a long kind of slope and then a very short spike, and then a long slope and a very short spike. And so that's another example of pathological order, where usually the state of the brain is to kind of have this near white noise to it, where there's just this almost random firing happening in the brain. But when you have this synchronization across parts of the brain that shouldn't be there, you have these pathological states that a person gets into. Any comments?
The interesting thing about that, I got to go soon anyway. I just want to make this last point.
Yeah, I think we're pretty close to being done too.
So the interesting thing is, so finally at the end of all this, so they talk about all these systems where everything goes crazy, and they're like, see, everything goes crazy. The physics doesn't seem to work. And it's just an introduction, so they're not really telling you how we actually make it work at this stage, except to give you an idea about the simplest physical systems that you can imagine, even with like 2 and 3 bodies in them, can become so complex that you can't use regular physics or math to sort of do anything. And so it seems like they throw their hands up in the air and say everything goes crazy. But at the end, they actually show you that this kind of random behavior where everything moves around, this kind of chaos, actually leads to higher functionality, especially in people. So you can imagine, for example, like just a person thinking about something. So you can imagine if their thoughts were completely ordered and completely focused. So you think about like the best way to do something. It doesn't really matter what it is. And you come upon something which seems to work. Well, then you'd be fixated on that one thing, and you'd never ever move off it, so you would never ever improve. But imagine that that doesn't happen. That yes, while you think about that solution most of the time, other times your mind just wanders off randomly, and you bring in just random ideas. Well, if there are other solutions that are out there better than the initial one, you're going to be more likely to hit it if your mind does wander around. This kind of chaotic motion inside your brain actually leads you towards a much higher probability of getting better solutions. That if you had such a really high Titan focus that you only brought in a very narrow range of ideas, you'd have a very low chance of ever hitting an idea that worked. And once you hit that idea, you would never ever move off it. You would never ever improve.
Very well said. Well, I don't know. I think that's possibly a good note to end our talk on. Just the fundamental unpredictability of chaos is fascinating. There's many very simple systems that exhibit chaotic behavior, and I think that we've gone through quite a few really fascinating examples of it. So thank you very much for the participants, and we'll see you next week.
Well, wait, what's going to be next week? Maybe you should tease that.
Oh, sure. So let me see. I completely blanked on that.
Isn't it bio stuff?
So it's basically the application of this to biological systems. What patterns
Right.
do we see in biological systems, and what's the underlying essential science or behavior of them which causes some of the concepts that we've actually been talking about?
Right, exactly. Ah, yeah. So we're gonna go into like spots and stripes and all sorts of other things, checker patterns and that kind of stuff. So that'll be good. But thank you so much, and hope you guys enjoyed.